Hi, I'm Xin Yuan, graduating mechanical engineer. I was the mechanical design lead for Bumblebee AUV 4.0, in charge of the overall hardware system design and worked on the metal 3D printed battery house.
My name is Chan Wai, and I'm the mechanical co-lead for Team Bumblebee 2021. I spearhead the team's mechanical development and assist in the testing and improvement of our full range of vehicles to ensure seamless co-deployment.
Hi, my name is Delvin, and I am a senior student studying mechanical engineering in the National University of Singapore. I am also co-leading the mechanical sub-team for Team Bumblebee 2021, and I guide the development of the vehicles to ensure that they are mechanically capable of performing the various competition tasks.
For the 2021 RoboSub competition, we plan to deploy both our AUV 4.0 and AUV 3.99. The BB AUV 3.99 was entered in RoboSub 2019 and is currently a stable platform. The BB AUV 4.0 is a ground-up redesign of the mechanical and electrical system, featuring a smaller rectangular hull with integrated electrical components. Its hull design is optimized for space and weight, eliminating the weight penalty incurred by the AUV 3.99 and allowing it to maneuver around tasks with space constraints.
In the design and development of our new autonomous underwater vehicle, we took a vastly different approach to that which governed our previous vehicle, BBAV 3.99. Through multiple rounds of iterations and modifications, BBAV 3.99 had begun to get heavier and larger over the years. This took away from the speed and agility that the AUV could achieve. We sat back down at the drawing board and sought to design a streamlined, competition-focused vehicle without excess. Our new vehicle, creatively dubbed BBAV 4.0, was the result of this 2-year-long effort to improve and to stay lean. The main hull of the BBAV 4.0, which was CNC machined from aluminum, houses all the electrical components. Its rectangular design emphasizes efficiency and compactness, allowing for much better utilization of its internal volume in mounting rectangular circuit boards. Through the use of performance analysis tools such as finite element analysis, the design was further able to be optimized, featuring internal lattices which allowed for much thinner walls while retaining structural rigidity and a full sensor suite and a host of other capabilities. Cooling of the SBC was done through the use of thermal adhesive and to thermally bond the SBC as well as our embedded GPU to the machine hull, allowing it to act as a heat sink, dissipating heat to the much cooler surrounding water. This design allowed for no additional cooling hardware while fully utilizing the design of the hull as well as the operating environment.
We pushed the limit further of reducing BBAUV 4.0's weight by experimenting with metal 3D printing. The vehicle's battery house were designed with internal lattices within the walls and an iso-grid pattern for the base, and this maximized the rigidity to weight ratio as compared to other manufacturing methods. Although there were initial struggles in waterproofing the hull due to its rough and uneven texture, through subsequent iterations and surface finishing, the hull was successful and achieved a depth rating of up to 35 meters. The battery house are also directly connected to the main hull using a subcon connector and are supported by crossbars with pins that can be removed with ease. The direct connection minimizes any excess wires, and this helped to reduce the overall weight of the vehicle. Being compact and lightweight, the BB AUV 4.0 is well suited in completing the tasks that require more maneuverability, such as rotating swiftly in the with Moxie task and gaining style points in the choose your side task. This vehicle will also be used for the catch or smash task, given its small size to pick up the objects and surface within the octagon. The BB AUV 4.0 will hence be deployed first to quickly complete the with Moxie task and move away from the dock before the slower moving BB AUV 3.99 gets deployed. To further support our competition strategy, we came up with different features that will give us an edge during the competition. The main hull of the AUV contains buttons for starting and stopping the mission, as well as resetting the vehicle at any point of time. The buttons allow us to communicate with the vehicle without having to spend time setting up the data cables, giving us more time to focus on the competition objectives. We also installed waterproof and pressure-tested lights to show the state of the vehicle during the mission, and this helps us to ensure that the vehicle is functioning as intended during its deployment.
During the brainstorming phase, We came up with multiple ideas for our new AUV's main hull. One of them was to manufacture individually milled walls, joined at the ends by fasteners and sealant. However, this design required manual application of sealant, which introduced human error as a possible factor of failure. Another idea was to incorporate a large window with an X reinforcement or similar bracing to support the acrylic display panel. Although this panel still allowed for us to have a look at the status display inside the AUV, we realized that the bracing would block a significant portion of the display. Furthermore, from FEA analysis, we found out that this design was susceptible to failure from internal pressure when the hull was pressurized. Mimicking the design cues taken from our metal 3D printed battery hulls, we explored the use of an iso grid to reinforce the flat hull walls, allowing for a reduction of wall thickness and hence a reduction in the overall weight of the hull. Despite the benefits that this design offered us, we soon came to realize that milling iso grids required numerous interrupt cuts, which increases the machining time, leading to an overall higher fabrication cost. The complexity and size of the main hull also meant that metal 3D printing would not be feasible. We decided to simplify the design, opting for a more conventional system of internal ribs to allow for the hull to be milled in one piece. Instead of immediately sending our finalized design for CNC fabrication, we decided to prototype our main hull using 3D printing. This allowed us to obtain a scale model of our main hull within a short period of time, with minimum cost incurred. This model allowed for us to test fit the cables and connectors and figure out any underlying issues with the hull design. Once the model was determined to be accurate and suitable for our usage, we sent our design for aluminum CNC milling. To ensure reliability of the AUV's hulls, BBAUV 4.0 was pressure tested at 3 bars of pressure in a pressure testing tank. This ensured that the vehicle maintained its original design goal and ensured the reliability and longevity of the O-ring seals. A hydrodynamic model of BBAUV 4.0 was generated from numerous CFD simulations conducted, aiding in not only the optimization of the design, but the tuning of the PID controller as well. This was done to ameliorate COVID restrictions, with simulations as well as the resultant hydrodynamic models yielded from CFD analysis being used to allow for near replication of real-world conditions to allow for continued controller testing and tuning.
Despite the limited pool time available during the COVID-19 restrictions, we managed to secure some slots with our school pool for testing of our vehicles. We compensate for the reduced pool availability by coming up with a more efficient overall vehicle design. The top cap of the AUV contains an internally removable sonar connector, which allows for quick and easy debugging when we are testing the vehicle at the pool. Another feature that we added is the quick disconnect pressure connector, which enables us to quickly respond to any drops in internal pressure during our pool test. Our LCD screen, which displays important variables such as hull pressure and battery voltage, is easily removable, which allows us to fix any technical issues immediately and proceed with the pool test. Our batteries are switched on and off using a magnet, and this allows us to hot swap the batteries more efficiently. The PCBs within the main hull were designed such that it was easy and quick to slot in or pull out from the mounts, thereby reducing the time taken to debug any problems. To fine-tune the buoyancy of the vehicle, we designed a customized float that can be attached on top of the AUV, depending on our needs during the software test. During bench testing of the BBAUV 4.0, the IMU magnetometer readings were found to be inaccurate due to the magnetic field generated by the water cooling pump's DC motor. After various failed attempts at resolving the problem, such as encasing the motor within a steel box, it was decided for the liquid cooling system to be removed from the AUV. The components are closely packed within the main hull, and hence any magnetic noise generated within the hull will significantly affect the IMU. This was the reason why we abandoned the liquid cooling and switched to the direct cooling method mentioned earlier. To evaluate this cooling solution for the AUV, a 1-hour stress test was conducted on the Jetson Xavier and SBC to observe their maximum temperatures reached. The results were positive, with both GPU and SBC not exceeding 68 degrees Celsius and were well below the recommended maximum temperature of 80 degrees Celsius for the required processing speed.